Hi everyone, I am Naina Goswami, a MinEx CRC PhD student at ANU, and I will be presenting my work on the Sub-solidus replacement of rapakivi textures at Mannum Granite. This work is supported by the MinEx CRC, which is funded by the Australian Government's Cooperative Research Centre program. Mannum is a historic town on the west bank of the Murray River in South Australia with a rich history. The area was inhabited by local Aboriginals, and the first paddle steamer named Marianne was built here, and since then the town is known as the birthplace of the Murray River paddle steamers. But the area also has a rich geological history. It has been widely studied by many geologists in the past and is part of the Delamerian Orogeny fold belt, which is one of the most important tectonic units in the history of Australia. So study of Mannum Granite forms a part of my PhD project that aims to employ argon-argon geochronometer to understand the thermal evolution of the Delamerian Orogeny. This project is in collaboration with MinEx CRC. The samples from different areas within the region are selected on the relevance of timing of different events within the fold belt, of which Mannum Granite is a crucial part, as it is a post-Delamerian A-type granite. This slide is just to give a brief introduction to the Delamerian Orogeny. The fold belt was formed during the Cambrian period and has a complex thermal and metamorphic history, hosting variety of lithologies, both deformed and undeformed. It is sparsely exposed in Australia, with evidences in other parts of the former Gondwana land. The orogeny is host to copper moly gold porphyries and has suffered varying degree of metamorphism and alteration styles. Mannum Granite is part of the porphyritic granite suite consisting of varied post-Delamerian granites and volcanics. It is an important unit within this suite as it is an A-type bearing rapakivi textures. This unit has been extensively studied in the past by many renowned geologists, and there are several theories around its observed textures and petrogenesis. The granite displays good evidence for magma-mingling, inferred from the presence of mafic enclaves of varying shapes and sizes. The presence of myelolytic cavities within the granite suggests a high level of emplacement in the crust. Despite the wealth of data available, its petrogenesis is still debated, with theories ranging from fractionation of basaltic magmas to partial melting of crustal lithologies. Mannum Granite has very interesting microstructures and in some aspects different to what I have studied in the past. The grains have curved to lobate boundaries with interpenetrating textures owing to mutual interference or contact melting during growth. Now this is not a magmatic texture but a sub-solidus one. Variety of K-feldspar textures such as braided perthite, patch perthite, goes to fine-tuned microclines are observed. There is possibly two generations of K-feldspars identified as K1 and K2 in the image, separated by a plagioclase mantle. The K-feldspars have very fine, disseminated iron oxides, indicating their porous nature, and subsequent infilling by fluid inclusions during melt percolation. The presence of cuspid grain boundaries of biotites indicate their consumption during interaction with the percolating fluid. The presence of fluid is justified by the presence of sericite, calcite, and the grain shapes observed. This is further exemplified by titanite pseudomorphs that consist of sericite, calcite, iron oxides, and some relic titanites. Evidence for K-feldspatization is evident through the consumption of plagioclase to precipitate K-feldspar and the relic plagioclase island in coptical continuity with the primary plag core in the center. This last image indicates the eating up of K-feldspar by plagioclase, in which plagioclase melt, infilling through the cracks of fractures, eats up the grain from inside. Argon-argon ages were observed from this granite by separating K-feldspar and biotite and then subjected to step heating experiments. The samples show very distinct ages. Within K-feldspar, two distinct age reservoirs of 440 and 444 million years are observed, while biotite preserve an older age of 473 million years. I'll get to their significance later. Temperature time histories for biotite and K-feldspar from Mannum were reconstructed using diffusion data obtained from experiments. K-feldspars show rapid cooling from 446 to 438 million years, followed by slow cooling, whereas biotites show rapid cooling from 470 to 444 million years, with the introduction of thermal event at 444 million years, recorded by the coexisting K-feldspar but not reflected in the biotite age spectrum. We anticipate the maximum temperature of this thermal event to be 385 degrees C, as biotite begin to show a diffusional loss profile with temperature exceeding 385 degrees C. Classic evidences of metasomatic activity are present. Presence of alteration zone next to fault plains which are sericite-rich, 2 generations of K-feldspar separated by a plagioclase rim, disseminated sericite calcite, and irregular curved lobate and cuspate grain boundaries and interpenetrating textures indicate metasomatic activity. When thinking about the nature of the metasomatic agent, we anticipate it to be a hydrated potassium and calcium-rich fluid which is acidic in nature. The way by which this fluid would alter the minerals could be due to volume diffusion or dissolution reprecipitation mechanism, where a secondary phase is precipitated at the expense of the primary phase through a migrating reaction front, or it could be both. On correlating microstructures to argon ages observed, 2 interpretations can be made. The first one is where 2 thermal events have taken place, the first one at 444 million years identified as K1, and the second at 440 million years that formed K2, while biotite age can be interpreted as a cooling age ever since the formation of the granite. The second interpretation also consists of 2 thermal events, where the first thermal event is reflected through biotite age of 473 million years, while the second thermal event is at 444 million years, and 440 million years is a cooling age. At this point, we haven't decided which interpretation to go with, and we're still looking into it. Apart from the major thermal events, there is also evidence for late-stage tectonic activities, such as the intrusion of the mafic dolerite dike, which we had timed at 435 million years using the Argon geochronometer. We also observe honeycomb weathering and reddening of K-feldspars in the top part of the quarry, indicating of weathering and groundwater percolation altering the granite. So to say, the following inferences can be drawn from the study so far. There is concrete evidence of metasomatic activity at Mannum, where the argon ages reflect the timing of 2 metasomatic events. We anticipate 2 possible scenarios how this could happen. First, where the activation of the old teal flat shear zone east of Mannum, which we dated at 446 million years, could have been active and have served as a pathway for fluid infiltration. The second scenario includes the correlation of ages at Mannum to the timing of thermal perturbations in the late Ordovician Lacunar fold bed. As mentioned before, the study of Mannum Granite forms a part of my PhD, so obviously there is a lot more to do before we can concretely prove things. The idea is to potentially analyze more samples and conduct more microstructure analysis, and then use this data to interpret geological history in context of the Delamerian. More correlations with other units of similar ages can be made. The last step would be to document these interesting new results. And here are the references. And thank you very much.